Okay, well, thank you very much for the introduction, and also thank you very much for allowing me to speak, given that I was only able to come here for this very last day, and apologies to all the previous speakers that I unfortunately had to miss while I was teaching Hamilton-Jacobi theory to unsuspecting third semester physics students at ETH. Okay, so the context of my talk on gluing black holes, small black holes along timelike geodesics, is the construction of well, it's part of a program, if you wish, to construct many black hole spacetimes. And so the astrophysical motivation is, I suppose, fairly obvious. And so correspondingly, there already exist some explicit solutions of the field equations that describe such things. And so let me remind you of what they are. So explicit solutions, they, as far as I know, only exist in the Einstein-Maxwell case. Okay, so these equations I'm not going to write down. So Ricci curvature equals some electromagnetic stress energy tensor, and the Maxwell equations hold. And these are known under the name of, so apologies, I don't know how to pronounce the name correctly, Majumdar-Papapetrou, that found them, I believe, independently in the 1940s, 45 and 47. So basically they found the correct ansatz for the metric and the vector potential. So we'll just write it down because it's so simple. So omega to the -2 of x dt squared plus omega squared x dx squared. So that's the Euclidean metric, dx squared here. And the vector potential is omega of x reciprocal times dt. Okay, and if you stick this into the Einstein-Maxwell equations, you will find that you get a solution if this scalar function omega satisfies the Laplace equation on Euclidean 3 space. And of course, for that equation, you can construct many solutions. You can just write them down. And so these Majumdar-Papapetrou solutions you get if you just take a superposition of shifted versions of the fundamental solution. You have mass divided by x minus xi over i's. It could be a finite sum. If you're a mathematician, you can make it infinite. So this satisfies the equation away from the punctures, and so then it's well known that if you only have n equals 1 of these black holes, then it's a version. So that's a extremely Reichenau-Nordström metric in suitable coordinates. And in general, it's supposed to describe n many extremely charged black holes. And so you see the solution here is static and very rigid because that's the only thing that you can possibly do. I should add a +1 here to make the metric asymptotically flat. Okay, and so that's the first one. And there also exists a generalization, which is perhaps less well known, to the case of positive cosmological constant, and it's called the Castor-Truschen solution from '93. And so, of course, lambda could also be negative there. But as far as I know, that's it. As far as explicit space-time solutions are concerned that describe, in some sense, several black holes. Okay, so if that problem is too difficult to solve, explicitly, then you could try to pass to the constraint equations and instead try to construct initial data that contain several black holes in some sense. And okay, so explicit initial data are actually equally scarce. And the best that I could find is something that Miesner and Brill and Lindquist did in the 60s. And so let me just write down one thing that they do. So I'm going to call the initial data in my talk gamma and k, so the first and second fundamental form. So they construct your time symmetric initial data, so k is equal to 0. And gamma is again given using a conformal factor now to the power 4 times the Euclidean metric. And again, omega has to satisfy the linear Laplace equation on R3. And so you get the same types of solutions. And then you can do some identifications and quotients by spherical inversions and whatnot to get sort of more interesting topologies out of that. But again, this is very rigid and explicit. Okay, and so if one wants to have more interesting data, one should consider more powerful techniques that go beyond explicit solutions. And that's, of course, the method of gluing. And so from the program, I gleaned that Stefan Cime, for instance, already gave a talk about gluing for characteristic initial data. So before I get to the initial data version, let me just mention in shameless self-promotion a result for gluing on the space-time level that I produced some years ago. So the space-time level, I have a result that was, I think, published in 21, in which I construct many black hole de Sitter spacetimes. And let me just draw a picture rather than giving the precise statement of what that looks like. Namely, so first of all, de Sitter spacetime, you can imagine here as being the product of time and the three-sphere. And the metric is such that the three-sphere expands exponentially fast. So cosh square t as time goes to plus infinity times the usual metric on the three-sphere. And so I'm going to sort of illustrate this, these metrics here by drawing a three-sphere. Yes. And the way that these spacetimes are constructed is that you take some points here. So let's take this one, P1, perhaps that one down here, P2, and then one in the back, P3. And at each of these points, so around each of these points, you draw a little ball. Okay? And as time goes on, these balls, remain of fixed size here in the three-sphere, so they expand their volume, let's say, expands exactly by the same factor here. And then for each of these points here, you decide on parameters mass and angular momentum, also here and also there. And they're subject to certain balance conditions. So somehow some weighted sum of the mass, weighted sum of the points weighted by the masses has to be equal to 0. And something similar for the angular momenta. But what you can then do is construct a metric that is isometric to the Kerr-de Sitter metric around each point with the desired parameters. So you have to think about how to sort of orient the angular momenta. You also have a choice to do that. And then away from these open neighborhoods of these points pi, the metric, so let's call it G, the metric is roughly equal to this de Sitter metric that I wrote on over there, this de Sitter metric, up to error terms that decay like cosh to the -3, so they decay exponentially fast. Okay, and so this is perhaps a stretch to call this a many black hole spacetime because, as you know, in de Sitter space, any two fixed points here on the three-sphere will eventually be out of causal contact, so you cannot send a signal from this one to that one. So there are sort of several black holes, but they don't talk to each other at all, so they're out of causal contact. But I'm going to immediately mention here that the construction is sort of in spirit closely related to Friedrich's result on the on asymptotic de Sitter metrics, where he prescribes asymptotic data at the conformal boundary. And so here, there's gluing happening for these scattering data at the conformal boundary, so t equals infinity, which involves the corresponding constraint equations, which in this case are linear. So there's already some gluing for constraint equations secretly happening underneath. Okay, and so now the real deal for initial data gluing started with the work by Corvino and Shane in the early 2000s. So 2000s. Which I will not get into detail for, but it's related to the underdetermined elliptic nature of the constraint equations and the overdetermined nature of the adjoint of the linearizations. So I'm going to have to mention one part of that in a second. Okay, and so this work had a big impact and led to a lot of further developments. I'm not going to write down all the names here. So Eisenberg was just mentioned, Mazzeo and Pollack for initial data what do you call it? Engineering, thank you, yes. And crucial and delay for sort of smooth localized gluing, and Carlotto-Shane for gluing in angles. Aretakis, Chimek-Rodniansky already mentioned for null gluing. And also more related to this talk, perhaps a paper by Anderson, Corvino, and Pasqualotto from earlier this year, where they construct asymptotically flat data with sort of widely separated lumps that are smoothed out versions of Brill-Lindquist, as a matter of fact. Okay, and so as far as the title, so the subtitle here, many black hole spacetimes, is concerned, the question is, of course, which one of these initial data might qualify to produce such spacetimes. And so there I want to mention this result by Crucial and Delay in their paper from 2003, where they construct initial data on R3, which are, so here's the origin. And so you select points, and then to each point you also select the negative of that point. And then at these points you fix your Kerr data, and then you have to take the same Kerr data, up to signs perhaps, on the other point. And the Kerr masses corresponding to the angular momenta have to be very small so that the gluing works. And so sort of in the neighborhood of these points you have exact Kerr initial data. Then outside of some large ball you also have Kerr data with mass and angular momentum determined by what you put in here, more or less. Yeah, and so these are the initial data that they construct. Okay, so they should certainly qualify as having many black holes initially. As far as the evolution of such data in the, using Yvonne Choquet-Bruhat's theorem is concerned, much less is of course known. So that's some of the drawback, if you want, from the space-time perspective of these initial data gluing constructions. It's very hard to control what the evolving space-time actually looks like. There is, however, in this case, a result by Crucial and Mazzeo from 2005 that shows that for these kinds of initial data, a sufficiently large part of the spacetime in the exterior region exists so that one can certify that the evolving spacetime has a disconnected black hole region. So there are several black holes in there. But it doesn't control what happens in compact regions, for instance. What happens to the black holes? Perhaps they merge or something. So that's not part of the theorem. Okay, yes, please.
The balance conditions for in your example C mentioned. What do they rule out? The balance conditions.
Yeah. So in the simplest case, so that's so if the angular momenta are all 0, so you just glue in Choquet-de Sitter metrics, then it is the following. So you really regard S3 as a subset of R4, so you can add points. And then the condition is simply that the sum of the masses times the points is equal to 0 in R4. And so this comes up as, so as I mentioned, what's happening here is that you take, roughly speaking, the asymptotic data of the Kerr-de Sitter metrics at the conformal boundary, or Choquet-de Sitter metrics at the conformal boundary. You just try to patch them together with the asymptotic data for the Sitter space itself. So there's some error term in the, like in the gluing region. And it turns out that solving away this error term boils down to solving a linear divergence equation for symmetric two tensors. That the linear divergence equation is exactly the what asymptotically the constraint equations become in Friedrich's setup for asymptotic de Sitter metrics. So they just become a linear divergence equation instead of some coupled system of nonlinear equations. And so the question is whether one can solve this linear divergence equation in such a way that one doesn't destroy the fact that one really wants exact Choquet-de Sitter metrics here, here, and here. So you have to have control on the supports, and that gives you some condition on some of this error term has to be orthogonal to some co-kernel, and that's something you can compute explicitly. And the co-kernel of the divergence operator is conformal killing vector field, so you just do computation. Turns out that this is exactly what guarantees that this co-kernel is missed.
Well, it's more difficult to think of it as a physical balance condition, as in the case of Majumdar, Papa Petru, or something like this, where you have.
So I must say that I don't have a good feel for physical interpretation, or even some sort of conformally invariant or whatever interpretation of this. So I didn't try to work that out. So I don't know if this is a physical interpretation. Okay, and so right, I want to mention one more result on this initial data front that is then directly related to the space-time gluing that we're going to talk about, and that's the theorem by myself. So it's still a preprint, so I still hope it's correct. I think so. And what happens here is the following. It's a very general result. So basically, you start with any initial data. Let's say for the Einstein vacuum equations, possibly with lambda, but okay. Initial data, so you have some three-dimensional manifold X, and then the first and second fundamental form. And you also have asymptotically flat data, so that are defined on R3 minus some compact set perhaps. And I'll call them gamma hat and k hat. The task is, given a point P in X, you want to glue a rescaling of these asymptotically flat data, so you somehow scale it down to size epsilon, or mass epsilon if you want, and glue it into a neighborhood of this point P. And so to describe this, so in fact the theorem works in any dimension, but I'm just going to restrict here to simple special case for brevity. For special case, I'm just going to look at time symmetric data. And for illustration purposes, I'm going to take the asymptotically flat data set to just be the Schwarzschild initial data. So it's 1 minus 2m over, let's call it m hat. So everything asymptotically flat now gets a hat. 2m hat over r hat to the minus 1 dr hat squared plus r hat squared times the round metric on the 2 sphere. So this is a mass m hat Schwarzschild metric, and we'll glue a mass epsilon times m hat Schwarzschild metric into a neighborhood of this point in the initial data set. And so the theorem says the following. Namely, there exists a family gamma epsilon of initial data on X minus a little neighborhood of the point, right? Because the Schwarzschild data are singular, certainly at r hat equals 0. So let's take a little bit out. I'm going to write it as follows. Namely, X hat is less than epsilon times m hat I take out. And what is, X here. And what is X? These are geodesic normal coordinates. Around P. Okay, with the following properties. So first of all, such that, first of all, they satisfy the constraints. So gamma epsilon satisfies the constrained equations, which in this case just means that they're scalar flat. Okay, the second point is that away from the point P, these gamma epsilons converge to gamma smoothly with all derivatives. So I mean here that you take any compact set in X that avoids P, then you have smooth convergence over that compact set. Okay, but of course there's no uniformity as you get closer and closer to P. And what happens close to P is described best by passing to rescaled coordinates. Okay, so this gamma epsilon evaluated at a point epsilon times X. So this is a, let's write it like this. Right, I'm just writing it down in local coordinates, so it's a 3 by 3 matrix, and the ij component of that converges to the, let me write it at here, converges to the ij component of my Schwarzschild initial data here. And so this happens for bounded X hat. And I'm going to draw a picture in a second. Let me actually draw it right away. Okay, so if I try to illustrate this in a picture, I'm going to draw X as one-dimensional. The point P is here. So basically, if you look at the second point, what's happening is that you zoom in at your point P, which is, of course, given by X equals 0. You zoom in at this point at rate epsilon. So in other words, what you're looking at, so if I draw epsilon as another dimension here, you're basically looking at different speeds at which you can approach this gluing point P here. And these different angles of approach are exactly parameterized by X hat. And so out here, this is the regime number 1, your metric just converges to the original metric. And this here is regime number 2. Okay, so another way to phrase the second part here is as follows. that's equivalent to saying that gamma epsilon is roughly equal to gamma hat. So these are the Schwarzschild data, but not with mass m, but with mass epsilon times m hat. And this holds in the region where x is less than any constant times epsilon. Okay, so in that sense, you glue in a very light black hole in the neighborhood of this point P. And we make a more precise statement here. And a more precise statement, because I will draw that picture for the space-time setting again, is the following. Namely, so if you look very carefully, these two asymptotic regimes here do not describe the full story of how gamma epsilon behaves as epsilon goes to 0, because, for instance, you could approach at some like parabolic line or something like that that is not covered by either of these two regimes. So to get really full control and have no escape for gamma epsilon doing something silly, it's best to draw a better picture. And so I'm going to draw the following picture. This. Okay, so this is now what's called a blow-up, where I take the product of my spatial manifold X with the interval 0, 1 in epsilon, and I basically introduce polar coordinates around the point where the metrics degenerate or become singular at epsilon equals 0. And so that's the picture that I get. And so local coordinates, so it's a manifold with corners, and local coordinates suffice to describe this fully. So I have this near field regime here, where the lines that I drew earlier on the right-hand side are exactly these ones here. They now have perfectly separate limiting points here at the so-called front face at epsilon equals 0. Okay, and so in that sense, the gamma epsilons that I construct, they limit to the Schwarzschild gamma hat over here. And on the other hand, here I have another set of coordinates. Sorry, this would be x. And then here, this coordinate is exactly the reciprocal. So it's epsilon divided by x, or in other words, 1 over x hat. And then I also have coordinates floating around, which I'm suppressing in this picture. And so what you see is happening here is that once you're away from this front face, from this gluing point, so if you're over here, for instance, then your gamma epsilon is just equal to or converging back to gamma. Whereas in the singular limiting regime here, it converges to gamma hat. And so this picture now is more or less compact, right? And so you have full control also what happens, for instance, along these parabolic curves. They just limit to this corner here. So what's the statement? Namely, if you put together all the gamma epsilons into a single object on this bigger space here, x hat. So if you say that gamma tilde restricted to some epsilon level, said it's just this gamma epsilon, then this is actually smooth on this manifold with corners. So strictly speaking, there are some log terms, so it's log smooth on x tilde. So what this means is that, in other words, you have a family of these 3 by 3 matrices, gamma tilde, that depends now on epsilon and x. But if you write it down in coordinates, in these various local coordinate charts, it's actually a smooth. Each one of them is actually smooth down to epsilon equals 0, x equals 0, whatever you have. Okay, so this gives you full asymptotic control of these gamma epsilons, and that'll be important. Okay, and so one last comment about this, right? So you see that gamma hat, the Schwarzschild data, are asymptotically flat, so they limit to the Euclidean metric, right, when r hat goes to infinity. And the metric gamma into which you're gluing things in normal coordinates is, of course, equal to the Euclidean metric right at that gluing point P. So what you see in this picture, what is happening is that you glue an asymptotically flat data set, very small rescaled, into your original data set in such a way that the asymptotically flat Euclidean bit of the Schwarzschild metric exactly becomes the local infinitesimal Euclidean metric of the original metric. So somehow you're gluing in something asymptotically flat, which exactly matches the local Euclidean nature of your original data set. So that's why this gluing construction can succeed at all, because there's this matching condition between the two data. Okay, so yes.
Between the two data?
So it's simply that if I write it down like this, so gamma hat restricted to the to infinity, so that's right here, the boundary of R3, compactified, is exactly the same thing as gamma at the point P. So, you know, in the language, if you have a smooth manifold with corners, you want to specify a smooth function on it with specified boundary conditions, then of course you need that the boundary conditions match at the corner. And that's exactly what this statement here says.
Initial data engineering after Pollard, Eisenberg, and Piotr Kuschel. Initial data is connected by Schwarzschild links that are glued to
Different points.
Yeah. To different points. How is what you've been telling us different from that construction?
Yeah, so there's no wormholes or anything like that. It's really just a single black hole glued into a neighborhood of a point. So I meant, yeah.
It's just like not connecting the Schwarzschild to the other end of the neck.
Mm-hmm. Yeah. It's also exactly. Mm-hmm. Yeah. And so one thing that I didn't mention here, which is of course known to every initial data person, is that there is an assumption here that the metric gamma should be generic near P, so it shouldn't allow any killing initial data. Or alternatively, one can also modify the construction to allow for X to be the initial data of Kerr or Kerr-de Sitter, which of course does have kids, and the construction works still the same. But then when the gluing construction, this gamma epsilon, differs from the Kerr data set on some open set containing both P and a bit of the inside of the black hole. So there's a little trick there where one can hide the obstruction to solvability due to kids inside the black hole and then cut out that part where one couldn't solve the equations. But that's a separate story. So I just want to stress that this result applies when gamma is a Schwarzschild metric, or the full version with gamma and k, when gamma is a subextremal Kerr metric. And so if you just apply this result any number of times, you can glue into, you know, say a Kerr initial data set any number of smaller Kerr black holes. Okay, so now moving to the space-time setting now, sort of part of my numerology here. I'll continue then. So the space-time gluing on the nose seems, of course, strictly more difficult, and well, it appears to be strictly more difficult, because of course, if you succeed in somehow having you know, one space-time metric and gluing some other metric in there, then you can take any Cauchy hypersurface in the resulting space-time, you know, record your initial data there, and they will satisfy the constraint equations, and you know, will sort of glue together the initial data at that hypersurface of your original one and the one that you're gluing in. So somehow this is, you know, this has to accomplish more. Much more than any initial data gluing. So why is there any way in which space-time gluing could be, in parts, more doable than directly controlling the evolution of initial data sets of, you know, any of these sorts? The point to some extent is that one should not take the initial value formulation too seriously at all times during gluing construction, and I will try to illustrate in some simple examples what I mean by that. So in a way, one can accomplish many aspects of space-time gluing without having to worry about initial data and their evolution. Okay, so let me just write down the theorem from this year. And so it's again very analogous to the theorem I just wrote down, except on the space-time level now. So we start with mg, which is you know, everything smooth, of course, and this is globally hyperbolic. And say Ricci flat. You could also allow for lambda, of course. Otherwise, I wouldn't have written that paper. Then you have a curve C, which is a maximal timelike geodesic. And then it's basically all you need. And there's also, again, a genericity assumption. So let me just write it down. So either mg has no non-trivial killing vector fields, or what's also okay is that MNG is a neighborhood of the domain of outer communications of a subextremal Kerr black hole, or Kerr-de Sitter if you allowed for lambda. Okay, so the analogous assumptions here. Yeah, sure. Yeah, so near a point, just a single point on C. Yeah, thank you. Okay, and then you have to select what you want to glue in, which is determined by a mass parameter m hat and an angular momentum parameter a hat, which is a subextremal Kerr parameter. So under these assumptions, the following can be done. Then there exists, so first of all, I need to introduce coordinates yet again. So let t and x be Fermi normal coordinates along this curve C. So for this talk, it suffices to state that that means that the metric G in these coordinates is equal to the Minkowski metric right at the curve, which is then given by C is equal to the spatial coordinate origin. Okay, so locally the metric is Minkowski. I mean, right there, the metric is Minkowski. And then there exists a family of metrics, G epsilon, that live on the spacetime M, but you take out an, same thing, so an epsilon times M hat neighborhood of the curve. So perhaps I should have mentioned here explicitly what I'm taking out here from the perspective of the rescaled, the small black hole, it's X hat is less than M hat. And of course, that ball is contained deep in the interior of the Schwarzschild data. So I'm just cutting out some deep interior part. But the neighborhood of the horizon, for instance, is all included in the gluing here. And it will be the same thing here. So I just cut out something deep inside the black hole. But neighborhood of the horizon of the small Kerr black hole that will come into existence in a second will be included. Okay, that's that. So by analogy, we're there. So unfortunately, these G epsilons do not satisfy the vacuum equations just yet, but they satisfy them to all orders in perturbation theory. So it's a formal solution. And needless to say, a conjecture that I'm working on is that you can correct it. So I'm going to state it right away. There exists a correction term, say H epsilon, which is trivial in perturbation theory, such that you can correct this formal solution G epsilon by this trivial thing in perturbation theory to get a true solution of the equations. But well, it's difficult and it's not done. So let's see. So the second part is the following, namely G epsilon converges back to G away from the curve in the smooth topology. And the third part is now the really non-trivial aspect, of course, which is that if I look at the metric G epsilon at any point along my curve, here's my curve C, and I look at it at some point T here, and I want to look at it sort of in epsilon size ball or box around this point along the curve. So then I do it again with rescale coordinates by saying that G epsilon at T and epsilon times X hat, so the components of this G epsilon, converge to the components of, so everything gets now a hat, at the Kerr metric with parameters M hat and A hat at the point X hat. This happens, let's say, for bounded. So in the smooth topology for bounded X hat and T, so local uniformly along this curve, this happens. And so again, you can rephrase this by saying that G epsilon in some, any epsilon-sized neighborhood of any point along this curve becomes more and more similar to a Kerr metric with parameters epsilon M and epsilon A hat as epsilon goes to 0. Yes, please.
So if you had a cosmological constant, probably wouldn't change anything.
Exactly the same. It's just the same.
And this problem is, of course, black hole stability, right? So
it's luckily easier than that.
is it?
I mean,
Because
well, I don't know. The
you
conjecture
have
is
to
still.
control this H epsilon, right?
Sorry, say it again.
You have to control this H epsilon near the horizon of this small black hole. Right?
Yeah, that's right. But notice that the limiting metric here is exact Kerr and not perturbation. So I'm going to make several comments that hopefully make that clear why I think that this would be doable without Kerr stability. Okay, so this is that, and the last bit is that I can draw an analog of this picture up there. Namely, I just take the product of that picture with time, and then I get the following picture. Okay, so this is now the time direction. Okay. Okay, so what is this picture here? So I have epsilon and x hat. So these are the local coordinates for my rescaled little black hole. Then I have the time coordinates floating around, and then I also have x and epsilon over x, or x hat inverse here. Okay, so you can cover this thing with some local coordinate patches exactly as up there. And the statement then is that the g epsilon, as a function of t and x, is really log smooth on this manifold with coordinates here. Okay, so all the asymptotic regimes are well controlled. And then you can rephrase these convergence statements here as something like the coefficients of this g epsilon, the g epsilon news, are smooth functions after log terms on this manifold with corners whose restrictions to this or that boundary hypersurface are the Kerr metric coefficients or the G metric coefficients. Okay, so it's stated very simply there. And so in this picture, there's already an indication related to John's question, which is that I require that these G epsilons are essentially smooth also in the time coordinate. But now if you look at the little black hole, so this is perhaps remark 1. Right, so the correct coordinates near the small black holes are these rescaled coordinates. So near the small black hole, you should use the rescaled coordinates x hat, so x over epsilon, which remain bounded when you're sort of a fixed multiple of the Schwarzschild radius or something away from the black hole. So correspondingly, you should also rescale your time coordinates. So if you consider a neighborhood of some fixed time t0 here, then you should use t minus t0 divided by epsilon to understand the dynamics at the scale of this small black hole near that particular time. But you see that I'm requiring, so the metrics that I construct are actually smooth in t, which means that, so function of t is the same thing as a function of epsilon times t hat. Right? So they actually, the dependence of the metric on time is only via the slow time and not via the fast time. That means that the small black hole at each instant in time, in the limit epsilon goes to 0, it's exactly the Kerr metric, not a perturbation thereof. And so in other words, what I'm trying to say here is that the small black hole evolves in a way that was described in the physics literature in the 70s by Hintz and others as quasi-stationary, or perhaps mathematicians would prefer a term like adiabatically. Yeah, should be an adverb, right? Stationarily, adiabatically. Okay, so there are no dynamics on the fast time scale.
So is this correct that you're saying in terms of a diagram, you just have to keep you're really keeping away from the light column, right? So the estimates you need for from the event horizon, right? So just have a well-separated region from the event horizon when you want to control this at.
It's a global problem, right? So if you just imagine you have this tiny Kerr black hole sitting here, then if some wave somehow propagates in from the outside towards the small black hole, it of course crosses the whole black hole immediately when epsilon is 0. So somehow when epsilon is very small, you really have to control the way that incoming radiation, even though it's sort of very small length, low frequency for the small black hole, you have to understand how it scatters off the little black hole. So you have to do the full scattering theory for the formal solution part. So I'm going to try to explain a little bit why for the true solution part. For the formal solution part, you don't need to do the full scattering theory, just zero energy is enough.
For epsilon going to 0, you get the geodesic hypothesis?
Yeah, that's right. So I'm going to add a few more comments here. Then I'll get to the other questions. Right, so I'm going to say it in words for reasons of time. So it turns out that if you have any family of metrics G epsilon that satisfies this, this smoothness condition that I wrote down over there, and you choose your black hole parameter m hat to be positive, so you actually glue something in, then necessarily the curve has to be a geodesic. And in addition, the mass m hat, I stated it like that immediately, but in fact, one has no choice other than to glue in a black hole with fixed constant mass m hat. And also the angular momentum vector has to be parallel along the curve. So somewhat one doesn't have any choices but to glue things in exactly that way. But I should immediately point out that
why should a Kerr black hole follow geodesic?
Okay, so let me immediately sort of mention things. I mean, the full proof is, you know, it's very non-trivial, but I can give you references apart from my paper. Namely, so there's a paper by Gralla and Wald from 2008 that, amazingly enough, you know, for me, actually assumes that you have a family of metrics exactly with these smoothness conditions over there, and then they analyze what one can say about the gluing, you know, along, about this curve C as a consequence of just solving the vacuum equations and having this particular smoothness property. And they already show that that C must be a geodesic, and they compute the first order correction in this gravitational cell force program. So this must be geodesic. But then older papers by D, so he has the most substantial number of papers about that, I suppose. So Berg, I suppose he started the business of matched asymptotic expansions in the physics literature. They already have several results that correspond to what I just said. So M is constant, and A hat is parallel. And D somehow does this using some precise analysis of the Tucholsky equation. And I admit that I didn't follow his argument carefully. But unfortunately, it's not a one-line argument that I can give you. It's some ultimately what happens. So the easiest proof, I suppose, from Gralla-Wald is that, roughly speaking, in some sort of limit, you know, what you're gluing in is, say, a Schwarzschild black hole. And so as a first guess as to what the glued metric could look like, you could try something like, you know, G plus 2 epsilon m hat divided by R. So if you start with the Minkowski metric and add this, then this is sort of 2 leading order. This gives you the Schwarzschild mass epsilon m hat metric. So if you take this and you see, you know, does this satisfy the field equations, you're in trouble because it's too singular and so on. But if you look at it on the linearized level, so you linearize the field equations around your metric and see whether this has any chance of solving the, you know, the linearized equations. And you do this, say, around the Minkowski case, then it's actually an exact calculation that you can do. And it turns out this is equal to some multiple times the Dirac delta times something like dt squared, give or take. Sorry, what do I want to say? Right. So this is the case when the curve is a geodesic, and it turns out that this is actually divergence free, which always has to be the case for you know, source terms of linearized gravity. If the curve C was not a geodesic, then you would have further terms here, which would not be divergence free. So there's some calculation of this sort where you can see that the geodesic. Yeah, so the angular momentum parallelness you cannot see as far as I know from such a simple argument here.
Just from what you've been putting on the board and explaining to us, I'm trying to retro-engineer. I mentioned this gluing result of yours. You sketched a special case also works for gluing in Kerr black holes. Is this a gluing that happens on the initial data level?
No, actually not quite. So it's not. So as I so this theorem does not follow from evolving the spacetime from those initial data. Okay, so I'm going to try to in the last few minutes explain a little bit of that. Let me just decide what to skip. So I should mention one more thing, just in words, that there is a paper by Young. He was a PhD student of Ron-Jansky's, I think, 2014, who considers the Einstein Klein-Gordon system, but the Klein-Gordon potential is somehow scaled as epsilon goes to 0 in such a way that some of the Klein-Gordon soliton, some focusing equation, the Klein-Gordon soliton somehow becomes small, extremely small in amplitude, so that the coupling is actually sort of very mild. And so he shows that you can sort of glue this little Klein-Gordon soliton along a geodesic. But the scaling is such that actually the metric even remains uniformly C1 across the gluing curve as epsilon goes to 0. So somehow a very regular gluing situation still. One last thing that I just want to remark here is that the fact that one glues in a Kerr black hole, whereas on the initial data level you could actually glue any asymptotically flat thing in, is related to black hole uniqueness conjectures. So conjecturally it's the only thing you could possibly glue in, because one can quite easily see that if you have such a family of metrics G epsilon that has this smoothness property, especially this smoothness, only involves adiabatically, then the local limit at each curve, this local limit here, has to be stationary because it doesn't evolve on the fast time scale, has to be asymptotically flat because it has to match up with the Minkowski metric, which is the ambient spacetime originally on the gluing curve. And ideally, it contains enough information, somehow all the way up to a neighborhood of to the horizon, so that you have a chance of having any well-posedness for wave equations and so on. So conjecturally, the only such metrics are Kerr. Okay. So somehow this theorem should be optimal as far as the conditions are concerned. Shouldn't be able to generalize that. No, so I say, what I do is actually put this in by hand and solve away error terms.
I understand. Yeah. To me, you've just answered, given a very serious answer to the question of why it is that we are gluing in Kerr.
No, I'm just saying that conjecturally I cannot do anything but that. But if somebody came along and gave me a stationary asymptotic flat blah blah metric, I could glue it.
Conjecturally, I'm sure just get the proof that it's the only thing that one might want to try, because nothing else stands a chance.
It might. So no, if there exists a asymptotic flat, stationary, Ricci flat with horizon and so on and so forth metric that also satisfies some nice mode stability type properties, then it should be possible to glue that in as well. It's not excluded by this. This would just be a new local model that you could try to glue along the curve. I don't know if such a thing exists, but no. Okay, so in the last few minutes, let me just try to, well, I suppose the question session is part of the whole talk, so let me continue for just 5 minutes. Comments about the proof. Okay, and so I already drew some part of the setup, right? So what we're trying to find is this G tilde, I already introduced in the gamma tilde version there, which is something depending on epsilon t and x in some way, so that the coefficients of this have the following property. So if I restrict them to, okay, so I should give these domains here a name. So if I restrict them to the original space-time except minus the gluing curve, or to the asymptotically flat bit times slow time. Right there, it should be the original metric G mu nu of T and X, and restricted to this asymptotically flat, local near the curve region. It should be the Kerr metric of the rescaled times. Okay, so I'm just trying to construct some, if you want naively, some family of functions, smooth functions, the coefficients of the metric tensor that have the desired limits. And so here you see, if you gave me something that violates black hole uniqueness, I could try to put that in here instead and see what I get. So the point is, since this naive guess, I just take any metric tensor that has the correct limiting behavior that already satisfies the vacuum equations to leading order, in epsilon at the original spacetime, and also to leading order along my curve. So in some sense, you could think of this as already being epsilon small. So you need to correct this, of course, by lower order correction terms. So it's in a sense an elaborate Taylor series construction. And so roughly speaking, you want to solve that this is of order epsilon squared. And so that's equivalent to the linearization of the Ricci tensor around G tilde applied to H being equal to this error term. The error term from the previous step without the epsilon. Okay, but if you look at this, you see that you have actually two different equations that you need to solve near epsilon equals 0, exactly because if you want the fibers of epsilon, the fiber over epsilon equals 0 is actually a union of two manifolds, the original one and the rescaled Kerr one. So really what you have is sort of two two equations that you have to solve sort of, in turn, one here, one there, and sort of construct Taylor series on a manifold with corners. So you have, two functions for which you have the Taylor, x to the j, y to the k, that sort of thing. So you have two equations. One is the linearization of the Ricci equation around the original metric g. So this is equal to some error. But so the interesting bit here, if you will, is that this error term typically is singular at the at x equals 0. So that's one equation, and the other equation is that you have to linearize the Ricci equation, the Einstein equation, around the Kerr metric g hat. It's called the corresponding correction term h hat, and this is also equal to some error term. And here the tricky bit is that you really insist that the construction produce a adiabatic metric. So the tricky bit here is that we want h hat to be a function only of slow time and the Kerr coordinates. So you do not want to solve this linearized Einstein field equation here on Kerr with a solution that has any time dependence on the fast time scale, because that would violate this adiabatic desire. And okay, so roughly speaking, then this second equation on Kerr amounts to understanding the linearized perturbations of Kerr at 0 frequency, right? So with essentially no time dependence at all. Okay. Yeah.
Because each of these problems has gauge freedom, right? And so you have to match, and you have to match these things. So what do you do with gauges? How do you match the gauges?
No gauges. Yeah, for the most part, no gauges. So in the, of course, ultimately you solve these equations and get smoothness and so on. You need to have gauges and ellipticity and something like that. But because I'm not solving this equation in any particular gauge, at each step I'm free to choose any sort of gauge that I want. That, and for many aspects of it, I don't need to worry about particular gauge choices at all.
When you want to make continuous or something, you have to worry about it.
Yeah, that's right. So essentially, yeah.
I mean, on some level, you're choosing Fermi coordinates about your timelike geodesics, so that is like a gauge choice.
It's just a choice of coordinates so that I can describe the main theorem, but it has nothing. But I'm not saying this is a very weak version of gauge choice, yeah. But it's sort of what Piotr is referring to, sort of more serious, because you want to make sure that your solutions depend continuously on smoothly on this time parameter for the Kerr problem and so on. So there are gauge choices involved eventually, but there's not one overarching gauge choice in which everything takes place. And also, given that I'm more or less out of time, let me just indicate in one. So for the first part, why gauges and fixed choices of gauge and corresponding the initial value perspective is not good. Okay, so let me just mention that here quickly. So toy model for the equation on the original spacetime, but with possibly singular source terms for the linearized field equations along the curve. So a toy model would be the following: you take the Minkowski wave equation for some function u, and you want to solve this equation here. And so if you insist on always doing initial value problems, then you could say, well, I'm going to take u at t equals 0 to be equal to 0 is my favorite function, and the time derivative as well. Let's look at that, for instance. But it turns out you can just solve this equation explicitly in the paper. I write down the formula. I forget now what it is. But basically, the picture that you get is that actually the solution of this initial value problem actually has a singularity emanating from the intersection of your Cauchy surface, t equals 0, and the singular curve, x equals 0. So right at this intersection, there's actually a, however weak, like C2 or something, singularity coming out. Okay, so that's what you get when you solve an initial value problem. And from the perspective of this gluing business, this is not desired, because it means that you have lack of smoothness coming out of some arbitrary point, namely the intersection of your arbitrary Cauchy surface and the gluing curve. In order to avoid getting any singularities along this light cone here, you have to fine-tune the initial data to all orders in powers of R. And so instead, what you can do is to just forget about initial values altogether and just regard this as an operator that turns out to be non-characteristic along the conormal bundle of x equals 0. And so you can actually solve this in two steps. Namely, you first solve this in Taylor series. So you sort of have a u1, which is a function of t and x. an angular coordinate, so you somehow write it in polar coordinates, and you can write some sort of Taylor series here, so r to the j times some coefficients uj of t, or something like that. You solve in Taylor series in r, possibly with some log terms. And the point is that the remaining thing that you need to solve is u1 plus a correction term u2 is equal to, well, you already solved this away to all order, so this is actually equal to something that is smooth and in fact vanishes to infinite order along x equals 0. So it's now just a smoothing. At this point, sorry, the correction term needs to satisfy this equation. And at this point, I'm happy to use an initial value perspective. So now I use initial data for U2 that are smooth, because now the solution of this initial value problem will be smooth. Somehow I solved away all the tricky bits along the gluing curve, and what remains is a smooth correction term. And this is the step, the only step in the construction where, in the Einstein setting, you actually need to worry about genericity and so on and so forth. Because in the Einstein setting, this is the linearized Einstein equation with initial data for the linearized problem, which need to satisfy the linearized constraints, but not with trivial right-hand side, but with some non-trivial right-hand side here. So the solvability theory for the linearized constraint equations enters here, and corresponding the genericity assumption. That's one bit. And okay, well, we just mentioned one final. So this somehow is an indication of why one has to avoid the initial value problem. And the second comment here is for the second equation, making sure that you can solve the linearized field equations with solutions that don't have fast time dependence. It turns out that there are obstructions to solving this equation, which are closely related to the existence of stationary solutions of this equation, like linearized Kerr and various other things, like linearization of mass, angular momentum, and center of mass. And so it turns out that one has to do a modulation at earlier steps in the construction. So somehow one has to basically choose the center of mass and the angular momentum parameters in earlier steps of the construction just right, so that at later steps, the error term that one gets here actually lies in the range of the linearized Einstein equation on Kerr on stationary tensor. So there's also modulation theory happening. Okay, so thank you very much. Sorry for running rather late. Yeah.